Hello again, it's the boring old Git once more, and this time we're looking at a Tektronix oscilloscope. Going back to 1973, Tektronix launched a new range of oscilloscopes, fully transistorized portable oscilloscopes designed for lab use. And for engineers of my generation, if you had one of these on your bench, you felt pretty good. The bottom of the range, the 465, which is a 100 MHz delayed time-based scope, became the de facto analog scope against which everything else was compared. The 475 was a slight upgrade to it, offering 200 MHz rather than 100 MHz bandwidth. The one we're going to look at, though, is the top of the range, the 485. This is actually a very different beast to either the 465 or the 475 and only shares numbering in common. The 465, when it was launched, was around $2,000. The 475 was a couple of $100 more, but the 485 was over $4,000. That's more than $22,000 in today's money. I think that's why there were relatively few of them around. I picked this one up off eBay for around £40 and then had to buy a replacement knob for the A trigger just to get the full set of knobs on the unit. When it arrived with me, it had a label on it saying power supply fault and a sticker saying return unserviced. So clearly this has failed in the past, been sent for service, and was sent back as uneconomic to repair. It's then clearly languished somewhere until it made its way through the system and onto eBay. So let's have a look and see what we can do with it. First thing is to check the fuses. So I took the top off the plug and lo and behold, no fuse. Of course, it can't be that easy, it never is. After replacing the fuse, it was time to try powering the unit up to see what happens. I've boosted the level of the audio so you can hear, but this does mean there's a lot of noise. Surprise, surprise, we get the ticking of a switch mode power supply in hiccup mode. So the first thing to look at is see if we've got any shorted tantalum capacitors. The reason tantalum capacitors are used on an oscilloscope like this is because they have a very, very high self-resonant frequency. An electrolytic capacitor is no good at the sort of frequencies this scope is operating at, and they would not give proper decoupling of the power supplies. The problem is that tantalum capacitors fail short circuit, so they will bring down any power rail that they're connected to. In a system with a linear power supply, they typically current limit when the short circuit is detected, so they will feed in their maximum supply current. This means the failed capacitor will tend to get very hot and can be quickly found because it's discoloured or even burnt. On a switch mode power supply, the overcurrent failure mode is that the supply temporarily shuts off and then comes back online. It means that you don't get the heating effect, so the only way you're going to find a failed tantalum capacitor is by going through each rail to find which one's shorted, and then going through every capacitor on the rail, taking them out, measuring them, if they're good, putting them back in. It's a long and tedious process. I didn't want to bore you by filming it all. So the video that's running is after I found the failed capacitor, pulling it out and testing it on the LCR meter. I did replace it with a similarly rated tantalum capacitor, which may not be a good move. I may have to upgrade it in the near future. At the time the scope was designed, they tended to use very tight tolerances for the voltage rating. They didn't run with much overcapacity. In this case, it's a 20 volt capacitor on a 15 volt rail. The modern approach would be to use either a 30 volt or even a 60 volt capacitor, as this will give greater longevity and reliability. So here we go, testing the culprit capacitor on my little tester. There was enough lead to be able to hook up onto the unit, though I probably need to sort myself some better ones out. Just trying to get it so it's being picked up by the camera and everything's visible and not shorting. Push the magic button. And there we go. 0 ohms. Give it another go just to be sure. Still 0 ohms, so we found the culprit. After fixing the capacitor, I powered the unit up and it was still ticking, albeit slower. I didn't manage to get any video of it, but one thing I did notice was I could hear a hissing sound and there was a smell of ozone. Going back to my days working with high voltage test and measurement equipment, it was classic corona discharge, which means that there is an issue somewhere with the high voltage system. Worst case scenario is that the tube has lost vacuum. Second worst case scenario is that the voltage multiplier has failed. Best case scenario is that there's damage to some of the insulation somewhere and that's allowing the corona discharge to occur. So the next stage of the process is to investigate that. As I start, I want to stress that you don't do anything with a CRT unless you know what you're doing. The accelerating voltage in a CRT like this is around 18,000 volts. If you get a belt off that, at the very least it's going to hurt. Chances are it's going to injure or kill you. So just to reiterate, if you don't know what you're doing, don't do it. This is the high voltage board from the bowels of the scope. It took me about half an hour to extract this from the unit. At the bottom is the transformer for the switch mode power supply. This has a 3 kilovolt winding which is used to drive the heater and the pre-acceleration before the deflection plates. The black module at the top is the voltage multiplier that generates the 18 kilovolts post-acceleration. The winding that feeds the pre-acceleration and the post-acceleration multiplier is fed via a resistor, and as we zoom in, I think this is where the problem lies. So this is the 1K resistor. Yes, it's 1K, not 3K like I said before. That feeds the multiplier and the pre-acceleration section from the winding of the transformer. That erosion is certainly not right, and when I started to take the resistor out, it broke in two. The erosion I don't think is wear because I can't see any corresponding witness marks on the metalwork that covers the module. What I think has happened is that the insulating post that supports the resistor has got pushed out of position in a previous repair, and this has pushed the resistor up close against the metal can that is earthed. The corresponding increased voltage stress has allowed the corona discharge to occur, and this has progressively eaten away the coating on the resistor, exposing the metal underneath. I think if it had been left much longer, then it quite possibly would have flashed over and damaged the oscilloscope seriously. I think we've caught it in time. Here's a microscope close-up of the resistor and also of the metal plate. I took these with my microscope, and you can see that while it looks like the resistor was worn, going in close you can see that much of it is a burn pattern, and correspondingly on the metal cover, if it had been wear, I would have expected the metal plate to be shiny, whereas in the area of the resistor it's actually showing signs of burning matching those on the resistor body itself. The original resistor is a 1/4 watt 1K metal foil resistor. I'm replacing it with a pair of paralleled 2K 1/4 watt metal film resistors. As I solder them up, I'm trying to avoid any sharp edges which would allow corona discharge to occur. I'm also covering the resistors in heat shrink to give a bit of extra insulation. What I've done with the mounting pillar is make sure that it's pushed firmly back through the housing where it fits, and I've epoxied it on the other side of the unit to the case. Hopefully that'll mean that it won't come adrift again and give a repeat of the problem. The other thing that I've done is, once everything was together, I've put in a good generous dollop of silicone. This is a really good high voltage insulator, and it's giving a protective cover between the cover plate and the resistor. So I've pretty much gone for belt braces and a piece of string to make sure that we don't get a repeat of this fault. So now it's back together. All we need to do is turn it on and see if we fixed the problem. I've got the high voltage to the tube disconnected, and I'm only looking to see if we stop the ticking and we stop the corona discharge.
Trust me. Okay.
As you can see, we've still got the ticking, so we've still got a power supply problem, but because the tube is disconnected, we can say that it's not due to that. Also, I'm not hearing any hissing and I'm not smelling any ozone, which suggests that the high voltage problem is sorted. To be able to move on with fault finding, it's worth having a look at the design of the power supply. This is the schematic of the switch mode controller, which is a custom Tektronix device. It's also used on the 7000 series oscilloscope and on the 305 data analyzer, which I'll be doing a teardown on at some point. We know there aren't any shorts on the power supply because I checked that and replaced the faulty tantalum capacitors. So the controller has two methods to manage the power supply and protect it. First of all is T1848 here. It's drawn as a transformer, and yes, it is a transformer. It's actually a current transformer, though the symbol here doesn't really give much indication of that. That's passed through a rectifier circuit and then into the current sense input here, which, when that differs significantly from the 7.5 volt reference, it goes into current limit and shuts down the output. So that one is the one that was being activated by the short on the power supply. If you listen to the two ticking rates, the one at the beginning is considerably slower than the one we were seeing at the end of the last section. I'm very confident that the one at the beginning, the slower tick rate, was due to the current transformer detecting an overcurrent situation. The other protection mechanism is the balance node. So the balance node here For the power supply to operate, that has to sit approximately at 0 volts. If it goes to more than plus 200 millivolts relative to ground, or more than minus 200 millivolts relative to ground, then the power supply shuts down. So what the designers have done is they've got a resistor on each of the positive power supplies and each of the negative power supplies. So if any one of these is out of specification, the balance node ends up outside its plus or minus 200 millivolt range and the power supply shuts down. The other inputs it's got are these over here. These are monitoring the beam current and the beam voltage. If either of those is out of spec, again, this will shut the power supply down. However, we know that it's not these that are triggering because the HV to the CRT is disconnected. So there is no beam current and there is no voltage being sensed. So both those lines will sit at 0 and have no effect on the operation of the power supply. So what we're looking for next is to see if any of the rails are coming up, but they aren't coming up fully, or the rails coming up and then overshooting its operating voltage. So this is the balance line. Unfortunately, the trace is AC coupled, so there needs to be a little bit of interpretation. But what you can see is that the transition when the power supply activates is around 400 millivolts positive. This is going to push the power supply into the trip condition. What it's telling us is either one of the positive rails is overshooting or one of the negative rails isn't operating correctly and is under voltage. So it's now a matter of going through all the rails on that basis. So now it's a matter of going through the rails in turn and having a look at them to see if they're doing roughly what I expect them to do. So first set, positive and negative rail looks okay. This one is 2 positive rails. Again, they're looking okay. One thing you've got to watch is that the rails may not get to their full operating voltage because the system's in hiccup mode. But these two are looking okay, so we can start thinking about moving on to the next set. And here we go. Again, these are looking reasonable. This is a positive rail and a negative rail. So moving on to the last set, which is the +5 and the -5. And we've got something very odd going on here. Both the positive rail and the negative rail are trying to go positive. This seems to be the root cause of the issue. So it's a matter of investigating what the cause of the problem is. So now we've got some sense of where the problem is, we can see if it can be fixed. What I'm doing is swapping the op amps in one of the known good rails. I think it's the +9 volt rail and the -5 volt rail that is giving problems. I know from the work I did on trying to identify shorts on the power supplies that the drive transistors on the regulators are working fine. So the problem has to lie in either the passive components or the op amps themselves, with the op amps being the favourite candidate. They're 741 op amps, and 741s of this era are known to fail as they age. I've seen multiple videos out on YouTube where people have found that the 741s have gone bad over time. So just trying to swap things over and then we can run a test. Push them in nice and tight. Hook the oscilloscope back up. And what I'm expecting is that the fault will move from the -5 volt rail to the positive rail. And this was a quite unexpected result because both rails seem to be working as I would expect now, which suggests that the problem was actually corrosion in the socket. I'm retrying it just to make sure. But one thing to note is that the power supply is still going into hiccup mode, but this is because I've only got the power board connected and there isn't enough load on the switching mode's power supply to get it to start reliably. So it doesn't indicate a problem, it just means that we've got to put everything together before we can properly try it. I apologise in advance for the lack of focus on this. For some reason the camera wouldn't grab a good focus. So turning it on, and we've got a trace coming up. This answers one of the big open questions that's been hanging over the repair so far, and that is whether the tube was good. We've got a good bright image. The focus isn't very good, but that's something that can be looked at. We've got traces for both channels. What I am noticing though, when I switch the bandwidth limit switch, there's a big delay on the lamp lighting up. This says that the switches are filthy and the thing needs a good clean. What I'm actually suspecting generally is that a lot of problems are going to be down to corrosion, dirt in the sockets, dirt in the switches. As I say, I can't get the focus as tight as I would like, and the brightness controls aren't working well, so that's something that needs looking at. I suspect as I'm playing with it, I'm running at the moment off the internal calibrator. As I say, as I'm playing with it, what I'm finding is that the scope isn't triggering, it's just free running. If the trigger circuits aren't operating, this could tie into the issues with brightness and focus, because the brightness control is linked in with the triggering and the time base, because it adjusts brightness levels according to settings and behaviour, particularly at the faster time base rates where it's got to boost the brightness to make the trace visible. Here I'm playing with the trigger and nothing's happening. I can't get the trace to trigger unless I turn it on to a free running mode. But what it's saying is that the basics of the oscilloscope are there, so in subsequent videos we can try and get it back up and running. Thank you for watching, and don't forget to like and subscribe if you like what you're seeing. Please do leave me comments, let me know how I'm doing, let me know anything you'd like to see differently. And thank you again for watching.